Cool. All right, B9d. So the question now is, right, what is the total pressure in the reaction vessel at equilibrium, right? So we're starting off zero point 0.3 atmospheres for everything. Part C, we already, determined that Q is equal to 3.33, which is far, far below what the K value is that we had calculated earlier in Part B. Right, the Kp value is 1.86 times 10 to the 12th. So we're talking about in the, what is that, trillions region is where the Kp is favoring product formation, whereas the Q right now is, not optimal. Right, it's at 3.33. So there's a huge gap that has to be changed there. And so, the way to approach this problem, right, to reach equilibrium is actually not really to necessarily use an ice table in the sense of setting it up for doing the reaction, right? In terms of like an equilibrium type of scenario, right, where we use the K values, because the K so strongly favors product formation, right? And we're so far away from K with our Q value, we can pretty much assume that this reaction is just going to go to completion, right? We're going to consume whatever limiting reagent we have, or limiting reagents, to convert them into NO2, and then from there, right, go through and do all of that, right? So if we're looking at what we have in these cases, in terms of, the reactants that we have and the products, right? What we're talking about here is for this reaction right here, where we have the same number of atmospheres, right? And we can kind of cut corners a little bit, right? Because we're talking about essentially something that's very similar to an ideal gas. So, the number of moles, right, would be similar in terms of the atmospheres, right? We don't have to go through that whole process of doing the conversions into moles, right? Because they would just still be similar ratios in all those cases, right? Because we're staying at the same volume, same temperature, and so forth. And so if we're thinking about that, right, what we can do is, no, that's what I get for messing around with the pen in my hand. I'm just gonna wait for it to reconnect. Hopefully reconnects in a second. Whatever, I'll just use my finger. Right, so when we're looking at these, right, we have 0.3 atmospheres of NO, right? We have 0.3 atmospheres of O2. We have 0.3 atmospheres of NO2 in this case. And so looking at what we have, right, the limiting reagent is going to be the NO gas in the formation of NO2, because it's the same number of moles, right? Because we can, basically, consider that the partial pressures are going to be the same, if we're treating these ideally and everything like that, right? So we have the same number of moles between NO and O2, but for every mole of O2 that we have to use 2 moles of NO. So we're going to run out of NO before we're going to run out of O2. And so, essentially what's going to happen is, we can then consider this to lose all of the 0.3 right there. We're going to lose 0.15 of the O2. But then in the case of the O3, right, we're going to then gain 0.3 in that case, right? So we'll end up then at the end, essentially with 0 NO gas, right? Technically there will be some. It'll just be, incredibly infinitesimally small that, right, because again, our Kp value is in the trillions, that, it may have a partial pressure of like 1 times 10 to the negative like 7 atmospheres, whereas everything else, is at least 5 or 6 orders of magnitude higher. So, in terms of thinking about what the total pressure is, right, that's going to be completely irrelevant in that scenario. For the O2, right, we can subtract this out, so, right, so we'll just end up with 0.15 in that case, and then in the case of the NO2, we'll end up with 0.6 atmospheres in those situations, right? So that's what the final equilibrium partial pressures are going to be, right? All the NO should be consumed, or, essentially consumed, right? Because it should basically go down to being, such a small amount that it can be completely disregarded. the O2 concentration should get cut in half because it will, be consumed. Half of it will be consumed in that reaction, right? But because it's not the limiting reagent, right? The NO is the limiting reagent in this case. You get that right there, right? And then everything gets converted into NO2. And so, we gain 0.3 more atmospheres of NO2. In that case, we end up with 0.6. So if we add both of those up, right, we get 0.75 atmospheres, right, as our total pressure in this case. And so that's how you would approach this specific problem right here. If the Kp value wasn't so extremely high, right? Let's say hypothetically the Kp value was, 18.6, right? So not that much different relatively, right, from the Q. In that case, right, you would have to go through the whole ice table and then using the K values, right, and then doing the appropriate appropriate quadratic equation setup thingy and everything like that. But yeah, so that's how you do this right here.